When it comes to electricity, we need to understand that a voltage source in a closed circuit will have two ends, a positive end and a negative end. The positive terminal is the longer one, whereas the negative terminal is the shorter one. While the electrons are actually flowing from the negative to the positive, we consider the direction of the current flow to be positive to negative. This is called conventional current. So, what does this mean? Conventional current is essentially the flow of current from the positive terminal to the negative terminal, and real current is the flow of current from the negative terminal to the positive terminal. The reason for that is because electrons are the ones that are delocalized and are free to move. Whereas in the positive terminal, obviously protons can't move, right? So positive charge doesn't move, it is negative charge that moves. Now let's cover the basics for electricity, where some of the basics are that power is energy per unit of time, resistance is measured in ohms, current is measured in amps, and voltage is measured in volts. Voltage is the amount of energy that each coulomb of charge has. Current is the amount of coulombs of charge going through a certain point per second, and ohms or resistance is preventing charge to flow. So again, volts is the energy, current is how many are going through a certain point, the rate, so energy, rate of movement, and the resistance reducing the rate of or the flow of electrons. Now, there are different electric circuit diagrams. This one is a very simple example of an electric circuit diagram, where you have the positive terminal and the negative terminal. We have a voltmeter here, which is connected in parallel, and voltmeters are always connected in parallel, and an ammeter, which is always connected in series. Ohmic resistors are the ones that represent a linear relationship between voltage and current. That is, the gradient is the same, and the gradient represents the resistance. Whereas for non-ohmic resistors, the resistance increases disproportionately with an increase in voltage. So this comes off of the equation V equals to IR. And it's saying that resistance is voltage divided by current. So if you were to graph a voltage and current, you would obtain these two graphs. One for an ohmic resistor and one for a non-ohmic resistor. The two main equations that you need to understand, because as I said before, we have V equals to IR. V equals to IR. And we also have what else do we have? Oh yeah, we also have this equation, P is equal to V multiplied by I. we said voltage is the amount of work done per coulomb, current is measured in amps, and resistance is measured in ohms, power is measured in watts, voltage in volts, and current in amps again. Voltage again is the amount of energy per coulomb of charge, current is how much is the flow of electrons through a certain point, and resistance is measured in ohms. So let's use the equations that we saw to kind of understand how to solve circuit problems. The first question that we have here is determining the voltage of the following circuit given that the size of the current is 0.2 amps. So how do we do that? Well, with the 100 ohms and with a resistance of 100 ohms and a current of 0.2 amps, we know that the equation is V equal to IR. So we can rearrange to get, we don't have to rearrange, voltage is 0.2 multiplied by 100, which is equal to 20 volts. How about some more complicated problems? Sometimes you might need to input one equation into another equation to find a solution. For example, given that we know that V is equal to IR, if you input that in here, that is equal to IR multiplied by I, which is equal to I squared multiplied by R, so it's I squared R. You can do the opposite. You can say current is equal to V divided by R. So therefore it is V multiplied by V divided by R, which is equal to V squared divided by R. Right? So those are two other derivations. For example, this question is asking, what is the power rating of the following light bulb? The power rating here will essentially be, we have voltage and we have ohm, so from the previous solution, we know that V squared on R is one way to find power, so it would be 240 volts squared divided by 1000 ohms. Will give us the power in watts. In that case, it is 57.6 watts. The solution is right there. Now, circuits can either be in series or they can be in parallel. Series circuits is when the resistance are connected in series. So it's given in the image below. There is no better way to say it. Because parallel, you can see what I mean by it. The resistors are connected in parallel to one another. Now, the equations that we have learned of V equal to IR and P equal to I multiplied by V still remain. The only problem that we have here is how do we calculate the total resistance of the circuit given that we have 3 resistors? In a series circuit, we add up the resistance. So the total resistance in a series circuit would be the resistance of one resistor plus the second resistor plus the third resistor. In a parallel circuit, we say that the total resistance would be equal to 1 on 1 of the first resistor plus 1 on second resistor plus 1 on the third resistor. So these are the two equations that we use to determine the total resistance of a series or parallel circuit. Now keep in mind that there might be combinations of this. For example, let's have a go at this question because I've also drawn a couple of questions just so we can have fun. They can get very complicated. So, how do we resolve the question that we have in front of us? Well, to resolve this question, we have to take it step by step. First of all, we need to solve what we have here. We have 2 resistors which are in parallel here and 2 resistors which are in parallel. If we solve those 2, then we will finally get 2 resistors which are connected in series to each other. So let's call this, we have R1, R2, R3, R4. Let's call this one RT1, 2, and then RT3, 4, right? So the total of 1 and 2 and the total of 3 and 4. The total resistance then would be adding up RT1, 2 plus RT3, 4, because those 2 would then be in series. The best way to explain it is by actually doing it. So let's have a go at this. RT1, 2. That would be 1 on 1 on 100 plus, I extend that, 1 on 250, which will equal 71.4 volts. It will equal 71.4 volts. Sorry, did I say volts? I meant ohms. Can I zoom in while I'm writing? I don't know. I'll try my best. Should be alright. No, I can't. I wish I could. Wait. Anyways, 71.4 ohms. 71.4 ohms, right? But that is only one. So our total now is 71.4 plus this part here. That one there would be 1 on 350 plus 1 on 200. In order to solve that, we would have 1 on 1 divided by 350 plus 1 on 200. That would give us 127.3 plus 127.3. So what would be the final value? So that would be 7.7 here. 1 and 7 is 8, 7 and 2 is 9. That would be 198.7 ohms. That would be the total resistance of the entire circuit, which is really important to calculate. But let's recap. What did we do? We found the resistance of these two parallel and these two parallel, because then we could simplify the circuit into something that is just two resistances which are in series with one another. How about this example? This example is a little bit more complicated, and it's going to take a little bit more time for us to cover. And this one is more complicated, and this one is even more complicated. So, let's start. How do we resolve this one? Let's start from the very beginning. What do we see here on the first square or the third square, depending where you're counting from? But we always try and find things further away from the two terminals, right? You can see that the 10 ohm here, the 10 here, and the 10 here are basically connected in series to one another. So the key here, the trick is to redraw the circuit, right? So if I were to redraw everything again now, and it takes a bit of time, I know that 10 plus 10 plus 10, I will write it here, 10 plus 10 plus 10 will equal to 30 ohms. So it's like having 30 ohms attached here, and then you have 30 ohms right here. You have another 10 here, another 10 here. You have 60 here. We have another 10 ohm here, and another 20 ohm here. The 30 and the 30 are parallel to one another, so we can solve that by saying that, well, RT is equal to 1 on 30, 1 on 1 on 30 plus 1 on 30, which is equal to 1 on 30 plus 1 on 30, which is equal to 15 ohms. So, let's redraw that all over again, right? Let's redraw it at the bottom, actually. Even though I want to use the bottom for work. This, as I said, this will take a while. And let's draw this one carefully. So we have 110 ohm here, 120 ohm here, 160 ohm here, 110 ohm here, 115 ohm here, and 110 ohm here. Now 10, 15, and 10 are connected in series, so let's redraw that again. we have 10 ohm here, 20 ohm here, $60 ohms here, and 10, 10, 15. Well, what is that? That is 10 ohms plus 10 ohms plus 15 ohms. That will equal to 35 ohms. So that is a resistor of 35 ohms here. However, the 35 and the 60 resistor are connected in parallel with one another. So you have to redraw that again. And basically take it very slowly now, because now it gets very complicated. You have 10 ohms at the top, 20 ohms at the bottom. What would be the total resistance there between the two parallel? It would be 1 on 1 on 60 plus 1 on 35. That means it would be 1 on 60 plus 1 on 35 that would be 22.11 ohms. So 22.11 ohms. Now let's add these ones up because they are in series, right? So to add them up, that would be essentially 10 plus 22.1 plus 20. That would be 10 plus 22, that's 32, plus 20, that's 52 ohms. Does that make any sense, guys? I encourage you to use the chat box function and I can answer your questions. Because the other two that we're gonna look at right now are insanely, they're quite a bit more difficult. So you might have noticed that the next one that we're gonna do seems like a simple variation of the one we just did, right? So just to recap, we started with a very basic circuit, series circuit. Then we said, well, we have a parallel, that's another basic one. We said that we can combine them to form a more difficult. That's one combination. This is another combination, even more difficult. This combination is actually significantly more difficult. In fact, I would argue it's more difficult than the one that you see here. But let's go. Let's learn how to solve this circuit. This one is really hard, man. So how do we do this? The circuit that you see here, I will redraw again. What you can see here is that unlike the previous, and I purposefully built the questions this way, unlike the previous circuit that you see here, where things were connected in series, then in parallel, then in series, then in parallel, then in series, and you found total resistance, which ended up being 52 ohms, 52.1. In this case, it's not the same. It's definitely not the same. Even though it looks very simple, it looks like the only variation that we have is this bridging resistor here. Now that is a massive change. It looks like it's not, but it is. And this is the problem with circuits, guys. The problem with circuits is that even when they look simple, they can be tremendously difficult to work with. Let's see how we're going. I think we're doing well on time, but we have 30 minutes to go. Enough time. Because these two are so complicated. So, why is it so complicated? Some of you might ask. And let me show you. What you guys are seeing here. Because what is this? Are they in series? Are they in parallel? Is this in series? Is this in parallel? Like, how do you decide? Where do you begin with? And the answer is the ones that I highlighted here are actually in parallel with one another. What we have to do in this case, we have to redraw the circuit. And it's going to look simpler. Now, this will take a bit of time. My drawing won't be perfect. So up until here, everything makes sense. Right, so as I was saying, this one is a bit more difficult because here we need to take into account how to redraw the entire thing. So it's 20 ohms here. $20 ohms here. Yep. So in this case, because this node and that node, so this node and this point here and this point here are the same, it's the same as drawing that part. I have to draw this multiple times. So this is like 30 ohms, but it's like saying this is 10 ohms, right? Is everyone cool with what I'm doing now? You can extend and you can say, well, this is 10 ohms. We have a 10 ohms here. And we have a 30 ohm right here. Yeah, perfect. This is drawn perfectly. So the reason for that is because it's very clear that this 10 and this 10 are in series with one another, right? What might not be so clear is that these two are parallel with the 30 here. The reason they are parallel, it's because this node and here are they the same, right? You can just extend that node, try and extend it, and you'll see what you will get as a result of doing that. I have to admit it's a little bit more difficult. It's difficult to explain, but these are wires. You can extend the wires, right? So you can extend that wire, and you can extend this wire, and then once you extend all of them, you will see that the circuit unfolds in a different way. But I will do something. I will do something really cool, and I will make it a bit easier for us. And I will change the value and make it 20 here. That way, it's easier for us to do the calculations. Let's start. The 10 ohm and the 10 ohm here. By the way, every number here represents an ohm, right? A resistance measured in ohms. So hard to draw with your finger. But yeah. So total the resistance of these two, they are in series. That would be 10 plus 10. So that would be around 20 ohms. Now the 20, if I were to redraw everything, that would be again 20 here, 30, just so you guys can get the right idea. $30 and this is 10 ohms. This is 20 ohms again. And this is 20 ohms again. Now the 20 and the 20 are in parallel, right? So it's the total resistance would be 1 ohm. It's actually the total resistance would actually be 1 on 20 plus 1 on 20. That would be 10 ohms, right? So you can replace these two with a 10 ohm. And I will redraw it again. You can replace it with one 10 ohm here. Now that we replace it with one 10 ohm resistor there, the 10 ohm and the 10 ohm can add up together to form 20 ohms. So again, erase, redraw, 20 ohms. The 20 ohms, which should have been there actually, can add up with, it's parallel to the 30 ohms. So that would be R is equal to 1 on 30 plus 1 on 20. That's going to be 50 on 2, so that's 25 ohms. So this thing here, we would have to redraw, and say that it is equal to 25 ohms, right? So the more simplified circuit, which is similar to what we've done here, so in the previous example, we would have a 10 ohm, another 10 ohm, a 25 ohm, a 20 ohm, another 20 ohm, and done, right? Obviously not the best drawing because you also have the 60 ohm here. So that would be again 10, 60, 20, 20, 10, 25. 25, 10, and 20, all of them add up together to form 55. So that would be 55 here. That 55 would be parallel to the 60. So that would be 55 plus 60 on 2. 55 plus 60 on 2, that is 115 on 2. 115 on 2. 115 on 2, that would be 57.5. But let me do that again, just in case. So 1 on. So the answer is 28 point. Sorry, my mistake. The answer is not 100. 15 on 2. The answer is 28.7. Oh, yes, yes. Yep, the answer is 28.7. I might have made a calculation mistake somewhere along these lines, but at least you guys get the general idea because I'm rushing with the calculations. But if I were to redraw it again, you would essentially end up with a very basic circuit of 10, 28.7, 20, so 10, 20, 28.7, you add them up together, should be 48, 58.7, something like that, 58.7 ohms, the total resistance. How about this circuit? So this circuit is actually a little bit more complicated but simple at the same time. With this circuit, the main purpose is to do this parallel. These ones are in series together. You add them up to form 1 ohm. The 1 ohm and the 2 ohm there are in parallel, so you solve that parallel there by saying 1 on 1 on 2 plus 1 on 1. So what you should get there is 2 on 3, which is 0.67, 0.67. It's actually 0.67 ohms for the total here. This one should be the same, 0.67, because we are mimicking basically the same parallel circuit. The two here are parallel to one another, so that would be 1 on 1 plus 1 on 0.5. So 1 on 1 plus 1 on 0.5. That would be 1 on 3, in other words 0.33. So what we're doing here is we're solving all the complicated stuff first. So 0.67, 0.67, this note here, 0.33. Now obviously this 0.33 here and this 0.5 are in series with one another, so that would give us 0.83. 0.83 would be this total segment here, which would be parallel to the 0.67 there. So that would mean 1 on 0.83 plus 1 on 0.67. All of it you have to reflect. So 0.67, 0.83. that would be 0.37 again, 0.37. So this entire node here would simplify to 0.37. Now, as it simplifies to 0.37, you can redraw the entire thing, because I think it's a bit more complicated now. You can redraw it, and it's gonna be significantly more simple than it was before, where you have 1 ohm here, 0.67 here, 0.67, 2 ohms here, and 0.33 here, 0.37 here. So 0.37 and 2, it's obviously 2.37. 2.37 parallel with that 0.67 there. So that is 1 on 2.37 plus 1 on 0.67. That is 0.52. And 0.52 plus 1, that would be 1.52 ohms. So I think today you will learn why in university no one likes circuits, or maybe you've learned that before. If you didn't know that, at uni no one really likes circuits just because of that. So yep. Other things that you are going to learn is in units 1 and 2 physics is about electrical safety. You are going to learn about fuses that can only be used once because they break the flow of current by melting. So what happens when it gets really dangerous all of a sudden and there is about to be a short circuit? Fuses basically break the circuit. There's another form that we call circuit breakers. By definition, their job is to break the circuit. They can be reset and they can be used again. There is residual